We're going to begin our integrals unit with a review of exponents and logarithms because we are now going to be looking at how to take derivatives and later integrals of these functions. Okay, so exponents, a couple of things to remember. If you have a negative exponents mean you take the reciprocal of the exponent you see. So negative exponent, reciprocal. Quick example, if we have 2 to the power of negative 3, this is 1 over 2 cubed, which is 1/8. If we have 2x to the negative 2, this is 2 times 1 over x squared, which is 2 over x squared. So please be careful and remember your order of operations, and that exponents, including negative ones, apply before multiplication. So unless there's brackets, it doesn't go in the denominator if you're multiplying. Okay, well, what if we have a fractional exponent? Fractions, I'm assuming you're in Calculus 12, you're probably okay with whole number exponents at this stage. So if we have a fractional exponent, we have a root. So let's look at an example there. If we have 8 to the 5/3. So the numerator states what power we're going to be raising the 8 to. So we're raising 8 to the 5th, and the denominator of our fractional exponent says what root we're taking. So we're taking the third root. It doesn't matter whether you raise to the power first and then take the root, or if you take the root first and then raise to the power. So in this case, we probably would prefer to take the root first and then raise to the 5th power. The answer is 32, but honestly, we just care that you remember how to do a fractional root. So the reason we do this quick review of exponents is because logarithms are inverses to exponential functions. So a logarithm, a log base b of a number, asks, what power do I have to raise b to get the number? So if we have log base 3 of 9 equals x, x is the power we have to raise 3 to in order to get 9. So one way we can do this is if we have the log in front and it's equal something on the other side, the base of the log is the base of an exponent. Okay? The number we have that we're taking the log of is what we're trying to get the exponential expression to be equal to, and the thing we have on the other side is the exponent. So I like this little down and then cross diagram. You have to be careful because it has to be set up in this way. Log base b of something equals something, okay, for that to work. But now we can look at it and say, oh, 3 to the x equals 9. So that means x has to be 2 because we know that 3 squared is 9, okay? And what we would say here verbally is log base 3 of 9. Okay, so log base 3 of 9. They're taking the log of 9. Let's look at another example of logarithms because these are actually a little bit fresher than exponents. You've only been doing them for about a year. Okay, for some of you it's been less than a year if you took pre-cal 12 this year. So log base 2 of 1/8 equals x. Let's use our arrows. So 2 is our base, x is the exponent, and 1/8 is what we want it to be equal to. Okay, so I know that 2 to the 3rd equals 8. If I want the reciprocal, I have to make my exponent negative. So here we have just 2 to the 3rd is 8. So 2 to the negative 1/3 equals 1/8. So the reciprocal is the negative exponent, okay? So that means x equals -3. Okay. So example 3. Okay. So A, let's look at log base 10 of 1. Okay, what is log base 10 of 1 equal to? Well, let's draw a little graph of what our logarithmic function looks like, and this again should be a review. So our logarithmic function has a vertical asymptote at x equals 0. We can't raise a whole number to a power and get 0 because powers involve multiplying or possibly dividing. So we can't multiply a number or divide it to get 0 unless we're multiplying by 0, which we're not. So comes up like this, and then the point where it crosses here is the base. Okay, sorry, is 1. And it doesn't actually matter what the base is. That point right there is always going to be 1 unless it's been moved around. So log base 10 of 1 equals 0. Why? Well, because 10 to the 0 is 1. And in fact, log base b, for any b greater than 0, log base b of 1 equals 0, because anything to the 0 power is going to be 1. Okay. So log base 10 of 0, we actually have a vertical asymptote here. Okay. So that does not exist. And why? Well, 10 to the x equals 0 has no solutions. We can't raise 10 to a power and get 0. And C, log base 10 of negative 1 does not exist. Okay, because you can't raise 10 to the x equals negative 1 has no solutions. You can't raise positive number to any exponent and get a negative number. Negative exponents just reciprocate. They don't actually make it negative. Let's look at another example. Okay, we're going to solve a few. Okay, so let's start with log base x of 32 equals 5. Log base 5 of x equals 3. You might see a variable in a few different places when you're solving a logarithmic equation. Okay, so what happens if the variable is somewhere else? We can still use our little arrow strategy. So we have x. The 32 is what we want it to be equal to, and the 5 is our exponent. So x to the 5th equals 32. Well, we can just take the 5th root of both sides. So x is the 5th root of 32. There's only one 5th root of 32, so x is equal to 2. Log base 5 of x equals 3, same. We can use our little arrows. So 5 to the 3 equals x. So 125 equals x. So log base 5 of 125 equals 3. And it's really good to keep this in your head. So log base 5 of 125, remember, means what power do I have to raise the base to? Do I have to raise 5 to get 125? Okay, so let's look at a couple other things. So one of the things, many of you will have scientific calculators that do not actually allow you to calculate any logs other than base 10 and base e, which we're going to talk about in the next lesson. That's called the ln. So if it says log on your calculator, generally it says 10. It is base 10. So we need the change of base rule so we can actually calculate things that involve logarithms that have bases that are not 10. Okay, so let's look at example 5. Okay, we're going to calculate log base 2 of 7 to the nearest. That doesn't really look like an n, does it? The nearest 10th. So change of base says log base a of b equals log a over log b. And actually, this is changing to base 10, but you can actually do it to base x. So log base x of a over log base x of b. Okay, and we can do log base 10. In this case, we're going to do log base 10. So log base 2 of 7 is equal to log base 10 of 7 over log base 10 of 2. And when we can calculate on a calculator, just log 7 divided by log 2 equals 2.8. Okay, so now we have a few more properties. Okay, here's another one, the equality property. So if log base b of m equals log base b of n, then m equals n. And this really is an example that log base b of x is a one-to-one function. So if you have a log of one thing is equal log of another thing, the things are equal. So how would that help me? So if I have log of 12x minus 7, and the bases do have to be the same here, is equal to log of 3x plus 11, I know that 12x minus 7 equals 3x plus 11. Okay? So now I can rearrange. I get 9x on the left side equals 18, and x equals 2. Okay? But I have to actually check to make sure, because remember, we can't take a log of 0 and we can't take a log of negative. So I have to check that my x equals 2 actually gives me a positive number inside both logarithms. Otherwise, this equation, it's not going to exist. Okay? So 12 times 2 minus 7 is 24, and 3 times 2 plus 11. No, 24 minus 7 is not equal to 24, is it? No, 24 minus 7 equals 17. And 6 plus 11 also equals 17, which is as it should be. So this has to be positive. Okay, so must not have a negative or 0 inside a logarithm. Because you can't say does not exist equals does not exist mathematically. If something doesn't exist, you can't say it's equal to something else that doesn't exist. They may not exist in two completely different ways. We can't say that. Okay, one more property. We actually have 3 more properties we're going to review. So this one is the product property. And each of the next 3 properties is related to an exponent property. So I'm going to write the exponent property first. Okay, so if I have a to the x times a to the y equals a to the x plus y. So however the property works for exponents, it's going to work in reverse for logarithms. So when we multiply exponents, it's like adding the exponents. Okay, so when we take the log of a product, so here we have a log of a product. So log base b of m times n is equal to log base b of m plus log base b of n. And that's actually one of the most useful properties, and it's one of the reasons that logs were heavily used. So people in like the 1950s used to come to, instead of a scientific calculator, which they didn't have, they would come to school with a slide rule, which would help them do large multiplications, because it's much easier if you know the logarithm of a number base 10 and you want to multiply it, all you have to do is add the logarithms, and then you get the logarithm of the other number. And so it would save you from having to do really, really long, big multiplication problems. Okay, so because adding is easier than multiplying. Let's look at an example of how this property, sorry, little history in there. let's look at how this is used. So let's say we have log base 2 of x plus log base 2 of x minus 2 equals 3. Well, we can actually simplify that to say this is equal to log base 2 of x times x minus 2, and that is equal to 3. Okay, so when we have a log equal to a number and we're trying to find an equation, the product property can go both ways. So you can use it to take a log that's a sum of two logs and write it as a product, as the log of a product, or you can go the other way and take a log of a product and expand it to be a sum of two logs. So here we can now rewrite this in exponential form. So we have a 2, that's our base. The 3 is going to come down and be the exponent, and the x times x minus 2 is going to be what it's equal to. So 2 cubed is x times x minus 2, which means 8 is x squared minus 2x. 0 is x squared minus 2x minus 8. And we can factor this. So we get x minus 4, x plus 2. Okay. And so we get two solutions, x equals 4 or x equals minus 2. But now we have to check. So if we use 4, 4 is positive and 4 minus 2 is also positive, but minus 2 is negative when we plug it in for x, and minus 2 is even more negative. So we have to reject this solution because it gives us a negative inside the logarithm. We don't necessarily have to always reject negative answers. If you're taking log of negative x, a negative answer is actually the only kind of answer that would work. You just have to check to make sure your answer works in the logarithm and doesn't give you a negative inside the logarithm. Okay, two more properties. So the power property is probably the most frequently used. So the exponent property this relates to is that a to the power of x to the y equals a to the x times y. Okay? So the power property for logarithms says that log base b of m to the p, some number to the p power, is equal to p times log base b of m. So if you have something that's raised to a power, you can pull the power down and multiply. Okay? We do need to make sure, just as with many other things in logs, that m and b are both greater than 0 and b not equal to 1. And this goes for generally for all of our logarithm rules. Okay? And we also have the quotient property. Okay, so again, this links the exponent rule, links powers and multiplication. The logarithm rule links powers and multiplication, just in a different way. Quotient property, we have log base b of a quotient of two numbers, m over n, is equal to log base b of m minus log base b of n. And our exponent property that goes with that is a to the x over a to the y equals a to the x minus y. So it's, again, we're linking division and subtraction. Okay, so example 8. And since we've linked in exponents, addition and multiplication are linked, division and subtraction are linked, dividing is how we get our negative exponents because division is linked to subtraction of the exponent. All very interesting. So let's say we have log base 4 of 3b. Oh, let's say log base 4 of 36, because I can't read my own handwriting and my 6 looked like b. So log base 4 minus log base 4 of 2x equals 2 log base 4 of 3 plus log base 4 of 2. Well, doesn't that look fun? So here's one where we're going to want to crunch it together. Sometimes we do want to expand it. This is not one of those times. So we have a subtraction. We can rewrite this as log base 4 of 36 divided by 2x. We're going to rewrite our subtraction of logs as a division inside the log. So subtraction outside goes to division inside. It's the opposite of the way the exponents work, where division outside goes to subtraction inside. Okay, so here, this is log of 3 squared, because we can take this power, this multiplication, and put it up as a power, and then we're adding, so that means we're multiplying. So this is log base 4 of 3 squared, that's from the first piece, times 2. So we're going to simplify that addition to a multiplication. Okay, so this gives us log base 4 of 36 divided by 2 is, okay, of 18, let's call this 18 over x, equals log base 4 of 3 times 2 is 9, 18. Because it's the same base, we can just make the inside things equal. So 18 over x equals 18, multiply by x, divide by 18, we get x equals 1. We take a look back just to make sure it works. We plug in 1 for x, we have a positive inside our logarithm. Everything is okay.